Hi everyone, I'm Fraser. I think most of you know me anyway by now. I'm going to talk about the FFI. So we're going to cover what's an FFI, and then we're going to look at the CFFI in Haskell. We'll have a bit of an in-depth look at a tool called C2HS, which is used to simplify writing bindings to C libraries. And at the end we'll just kind of have a roll call of a bunch of other tools and resources for using the FFI, but we're not going to cover them in detail. So an FFI, or a foreign function interface, is a mechanism to call code written in one language from code written in a different language. They're often used to bind or to wrap entire libraries, and typically those libraries are written in C or C++. You can use an FFI to export a routine, to use as a callback, for example, with another library, or some fancy coroutine work or something. We're not going to cover that tonight, but yeah, you can use an FFI in the other direction, so you're actually exporting functions you've written in one language to be called from another, rather than importing. Some important aspects of C, I guess. Who's familiar with C in the audience? Almost everyone, so you mostly will be well and truly across this slide. So header files are kind of like the public interface to a C library, so it declares various types, structures and functions. And so when you're using a library, you will include a header file in your file, and that will give you access to the types and the function prototypes and so on. There's a concept called linking, which takes object code which has been compiled, so from C or C++ into machine code. It'll contain references to the various symbols for the functions and types defined in that. And when you are using that code, after the compile phase, there'll be a link phase where your code will be assembled together with the library code. There's static linking, which basically smooshes it all into one big fat binary, and you can have extra copies of the library code floating around in every static binary. Or there's dynamic linking, where you have what are called shared objects, or DLLs if you're in from the Windows world. And those shared objects can be dynamically linked at runtime into the address space of the process of the executable that you ran. That depends on these dynamic libraries. And pointers are kind of essential C. Anyone who's done any C in earnest should be familiar with them. Basically, a pointer is a number that refers to an address in memory. You can have pointers to pointers, or you can have pointers to any kind of data structure, including primitives like integers or characters and so on. So Haskell's FFI, you enable use of the FFI with this language pragma. So language foreign function interface. This is the CFFI. There are some FFI independent modules that are provided in the base library, foreign.c.types. So you can use these modules without actually activating the FFI, but if you're using the FFI, you're going to need these because they're going to define the various types corresponding to the primitive types in the C libraries, such as C double, C uint, unsigned int, and so on. So to actually import a function, use foreign import ccall. This is the calling convention. Typically just ccall is what you'll be using. Unsafe, I'll discuss in a minute. And then the name of the header file, where the function is defined, and the name of the function. This can sometimes be omitted and inferred by the FFI. On the second line, we have a type signature. We have what we want the function to be called in Haskell. In this case, we're calling it C_sign. And we say it has the type C double to C double. So it's a pure function, takes one double, returns a double. That's the sign function. For stdlib.hrand, we're going to put that in the IO monet, because every time you call rand, it's going to hopefully return a different number. So here we declare the type of CRAN to be a CUint, so it's a zero argument function, but it's going to return a result in the context of the IO monad. So that the side effect, well, not a side effect, but the indeterminacy of the function is encapsulated in the type of the function. So this is, FFI 101. Safe and unsafe, so I promised to talk about that. I'll do that now. So the safe keyword, so there's two options here. You've got unsafe and safe. Safe is required when your foreign function can call back into the Haskell runtime. For example, if you're exporting a function as a callback. If you're importing a function to which you could supply a function that you've exported from Haskell to be called as a callback. Basically, any place where you could have a function re-enter the Haskell runtime, you need to use safe. Otherwise, things will crash and not behave properly. Safe is recommended when the foreign function could block, but it's not needed anymore. There's a concept called capabilities in Haskell, which is, I don't know a whole lot about it, but anyway, there used to be a constraint where the whole Haskell runtime had one capability, and if you did not use safe, if you used unsafe, then basically the whole runtime would block. But now Haskell has many capabilities, or multiple capabilities, so this is not as big a problem as it used to be, but it's still recommended. Safe has performance penalties, so there's extra bookkeeping and overhead that the safe function performs in order to have safe re-entrancy into the runtime and whatnot. And safe is the default. I've only really talked about safe here because there's not much else to say really, other than these are what safe does that unsafe doesn't. But unsafe is usually safe to use. So, unless you're aware that any of these are the case for a function you're calling, then it's fine to declare it unsafe, and you will avoid any of the performance penalties associated with the safe declaration. Yeah.
What are we saying that is safe or unsafe then? What is the thing that is safe or unsafe to do? Is it that it can't be used in concurrency, or?
Yeah, I'm not sure. There seems to be a consensus that these are confusingly named.
Yeah, right. Okay.
Within the community.
They have to be designed that way, otherwise you look at safe and unsafe and say, oh, I don't want to call it safe if I don't know what I'm doing. Whereas
sure.
Unsafe, if they called it faster, people would just use it.
Yeah. Well, maybe that's why
they had to give it a name to make it like stand out.
I think you're not saying that this function is safe to call, this foreign function is safe to call. You're saying that I promise to use this. No,
the extra safety stuff has been added to it to make it safe. Safety gear has been put on. Got a helmet on.
You can find commentary online and much discussion, I'm sure, about why the particular choice of safe and unsafe for this mechanism. But suffice to say, unsafe is usually safe, and you would usually want to use it unless you're aware of a situation such as the function could block or a re-entrancy concern. Okay, so pointers. This is just a made-up C library. So thing get version, which takes a pointer to a thing T, a thing type, just an opaque type. Char pointer, it's a C string. Thing get name, get the name of the thing out of the thing, and you pass a pointer to the thing. Thing new, what's this? So it's a double pointer. So this function here, you're saying I'm going to construct a new thing with this argument, the name, and I'm going to pass in a pointer to a pointer to a thing, and then thing new can allocate for and construct this object in memory, and then write the pointer to the thing inside the memory location given by this double pointer by the caller to the function. So yeah, it's a little bit convoluted, but that's actually a fairly common C idiom. And the return value is an int, which just will typically be 0 on success and non-zero on failure. So you can observe whether the allocation and the construction succeeded, for example. And thing free, so free takes a thing or pointer to a thing and frees the memory associated with that thing. So yeah, this is just a made up API. I've got some examples a little bit later that is close to this API but slightly different. Okay, so to actually write a binding to this API, we can include thing.h, and up on the top we will already have our language pragma for the foreign function interface and so on. You say foreign import C call thing get version. We're going to call it thing get version in Haskell as well. It's going to have the type pointer thing, so a pointer to a thing, and it's going to return a CUINT unsigned integer. Foreign import C call thing get name, and this is going to have the type pointer thing to a pointer CCHAR. There's a type alias for this in Haskell, which is C string. In C, a string is just a character pointer, and you're just going to move along the characters sequentially from where that pointer begins in memory until you hit a null character, and that's the end of the string. And if you hear of security issues caused by strings that weren't null delimited, or tried to read the length of a string from a buffer that didn't have a null character, and then you read past it and read all the memory that you're not supposed to read, or crash the program. But anyway, if you wanted to know how strings work in C, that's how it works. Foreign import equal thing new. So this one, if you recall, took a character pointer or a string, and it took a double pointer, so a pointer to a pointer thing, and the return value of this is going to be an IO C unsigned int. There's some functions for working with pointers and with strings. So we have with C string, which takes a Haskell string, and so it's the native string type. Its second argument is a computation that is parameterized over a C string, and returns an IOA for some type A. And it's going to return the result of that computation. So basically what this does is it takes your Haskell string, copies it to a C string, and then calls this computation with that C string and returns the result. Peak C string goes in the opposite direction, so it takes a C string and marshals that into a native Haskell string, and that occurs in the IO monad because there are allocations and whatnot. Peak dereferences a pointer, so we take a pointer A and it's going to return an IOA. And alloca takes a storable A. I'll talk about storable in a second. It doesn't take a storable A. It's got a type class constraint for storable A. It takes computation. It takes a pointer A, returns an IOB, returns the result of that computation. Okay, so what does it do? Storable is a type class that, among other things, gives the size of the data in memory. So what this is going to do is it's going to allocate some temporary memory of the size determined by the type A, and then it's going to call this computation with the pointer to that memory. And it's going to run that computation and return the result, and then alloca is automatically going to free that memory when that stack frame returns. Okay, so for actually representing opaque data, or possibly non-opaque data, in a C library in Haskell, we can have a new type thing, and we'll have the data constructor thing applied to a pointer thing. Now, it's worth noting this thing here, pointer doesn't actually contain a thing. This just gives us some additional type safety so that we can't perform invalid comparisons between different kinds of pointers, or do operations on one type of pointer with a different type of pointer. So for example, you don't want to be able to pass a thing to a free not a thing function. So this is just some additional type safety in order to prevent those sorts of dubious operations. Now to deal with this common C idiom of passing the double pointer and receiving in that location a pointer to a newly constructed object, we're going to use with C-string, because make thing takes a string, in order to get a C string that we can call the C function with. We're going to call alloca to get a pointer. Now this is going to be a pointer to a thing. Now pointer has an instance of storable. We didn't make an instance of storable for thing, but that's fine because we're not allocating a thing, we're allocating for a pointer to a thing. So we call alloca with this computation here, so these last 4 lines. What occurs in this computation, we call thing new, name and pointer, the double pointer. We get the result, which is an integer, or cint. If the result is 0, that indicates success. So we can return, or we can peek the pointer, so we look in that memory location. And then we apply thing to that, and just to that, so this is just the thing that you need. And then that's the result of this computation. However, if the result is non-zero, for example, you were out of memory and the allocation failed, then we can return nothing. For dealing with garbage collection, there's actually some really nice mechanisms in the Haskell FFI for being able to automatically finalize and free your objects when they're no longer needed in your program. So there's, as distinct from the pointer type, there's a finalizer pointer type. That's actually a type alias to a function pointer that takes a pointer A and returns an IO unit, which is typically a free function that's just going to return void. So that's what this represents. There's a function new foreign pointer, which takes a finalizer pointer A. So this is your free function or your destructor. Takes a pointer A and it returns an IO foreign pointer A. So what happens in here is basically you're taking a raw pointer and you're kind of wrapping that in a finalizer pointer. You're wrapping that in a foreign pointer and attaching a particular destructor to it. You can also add multiple destructors. They're going to be called in reverse order. So you use the function add foreign pointer finalizer, which takes a destructor or a free function and the foreign pointer and returns IO unit. And for unwrapping foreign pointers, there's the function with foreign pointer, which takes your foreign pointer A and then takes a computation that takes the raw pointer A and returns an IOB. It returns the result of that computation, having unwrapped the foreign pointer and passed the just the raw pointer value to that computation. So if we modify the example from a couple of slides back to deal with a foreign pointer rather than the raw pointers, so that when we're no longer needing the thing that we constructed, the Haskell runtime can free that memory on your behalf. So we import the finalizer pointer with foreign import SQL address of, that's what this Ampersand means, address of the thing free function, and its type is finalizer pointer A. Our new type changes to new type thing is thing finalizer pointer thing. Previously it was just thing pointer thing. And the only change that's needed in make thing is down here where we, after picking the pointer, apply new foreign pointer thing free to the inner pointer. And then we apply thing and then just. So there's actually very little code and very few changes needed in order to make use of the Haskell garbage collection to free your objects that are being allocated in a C library. Okay, a brief note on storable. So I mentioned that storable defined the size of the type A in memory. So size of takes an A and returns an int. It also defines the alignment, and peek and poke, which are used for marshalling the structure to and from native Haskell data types. So peek takes a pointer A, so just a pointer to this object in the C library, the object defined by the C library, and returns an IOA. And in the opposite direction, poke takes a pointer A, so the memory location you want to marshal your native Haskell data into, takes an A, that data, and returns IO unit. So this function will just write a memory representation of this Haskell data into memory. Okay, so C2HS. I think, yeah, I completely changed my talk a fair bit this afternoon. Well, I didn't change it, I just added a bunch of stuff. So I think I'll go through the next few slides and then I'll switch to some coding. So C2HS is a preprocessor to simplify the writing of bindings. So it lets you bind or easily kind of obtain types that represent enums and type defs in your C headers. It can automatically write your foreign import declarations for you based on which functions you're calling and how you're using them. And typically you'll find that these have a .chs file extension, and they'll output the .hs, and then that will be compiled in the normal compilation process for your program. Quick detour, not much, is a mail indexer. It's a program, has a library as well. It's written in C++, but it exports a C interface. And I've written a binding, which is very immature and you shouldn't use it, but if you're interested in helping me with that, that would be cool. Yeah, I kind of have a medium-term goal to completely replace Mutt with something I wrote in Haskell and has native tagging with not much and all of that. So anyway, some examples on the next few slides will come from my binding to not much. So for enums or enumeration types, in C it looks like this. So say type def, enum, and then just a bunch of, they're not constants, they're enumeration values. So this is kind of like a sum type of nullary constructors in Haskell. So is that sort oldest first, sort newest first, sort by message ID, and so on. So this is just an enumeration defining a sort strategy. And then the name of this type is not much sort T. So to reference or bind to this in Haskell, in your .chs, we have this declaration. So we have a curly brace with the pound and closed on the other side, enum, and then not much sort T as sort, so we can say the name of the type in Haskell. And here we can list 0 or more transformations of the enum values, so these things here. So we have underscore to case. Now when the preprocessor processes this, it's going to turn it into this declaration. So we have data sort, and then we've got 4 nullary constructors with names based on the names that we had over here. And then we derive enum. If your enum type has explicit numbering, for example, if you don't start at 0 for some reason, then it's actually going to write out explicit enum instances rather than deriving it. But if it's simple and you don't have any explicit numbering for your enum values, then it's just going to derive enum. For type defs of opaque pointer types, for example, so we have type def struct, not much message, not much message T is the name of the type. In the C2HS input, so the .chs file, we can have the pointer declaration, the name of the type that we're referring to with the pointer, because in this case we're interested in pointers to this type. We can say as message, so the name that we want to use for the type in Haskell. And then we say foreign new type, which is basically going to declare this as a foreign pointer, new type, and with a foreign pointer rather than a raw pointer. It's also going to give you a function for unwrapping that type. So we say with message, which takes a message and a computation parameterized over a pointer to a message, and returning an IOB. So what this is going to do is it's going to call with foreign pointer to unwrap that pointer, and then this computation is going to be called with the raw pointer, and the result is going to be the result of the computation. For calls, if we imagine we have a function here, well, we don't have to imagine it, there is actually this function in the not much library. Not much message, get message ID, so for a email message, please give me the message ID, which is a string, a const char pointer. And yes, the argument is a message pointer. So if we bind to it in this way in Haskell, so we say message get message ID, it's the name of our function in Haskell, it's going to take a message and return an IO string. So it's going to be called with one argument, which is a message, and it's going to say with message, message. And then we have this call declaration here in line, call not much message, get message ID, and we do it, closely composed to PXC strings, so we can actually get a Haskell string from the library, or rather we get a C string from the library, but then turn it into a Haskell string. Okay, so this turns into this code here. So all of this code is unchanged, except where previously we had the call declaration, we now have just the actual call to the function directly in Haskell. And it's going to have written this foreign import for us. So foreign import equals safe, not much message, get message ID. And then the name of the function, which is the same in Haskell, and it's going to take pointer to a message, return an IO for a pointer CCAR, or IO for a C string. So we didn't have to write this. Basically, C2HS took care of that for us because we just referenced the name of the function here in this call directive. And it says, okay, it looks in the header file, oh, I see the function you're calling, I will write the foreign import declaration for you. So it just avoids a bit of boilerplate. There's a few other tricks. So it's a common idiom in C libraries, because there's no namespaces, to just prefix every single function and type with the name of the library. So you'll have seen everything was prefixed with not much in the previous slides. So we can say context prefixes not much, and we can avoid writing not much at all. I don't know if this is a good idea or not, but I did it. Because it saved me keystrokes, which is not always the most sensible of motivations. But anyway, it's something that could be nice. Finalizers you'll have to manually attach, so you can use add foreign pointer finalizer to do that. And I also need to note, and we'll see this in the demo as well, that the pointer directive without the new type keyword will make a type synonym. And it'll be pointer unit, and you don't want that because that will allow you to use different kinds of pointers without any type safety. Okay, so I'll just switch to do some live coding. Yeah. Okay, so so this is my little C library I wrote. So we have a struct thing, but yeah, it just has a number, which is a serial number, and a string name. We have a function to construct a thing, so it's going to take 3 arguments: the serial number, the string name, and a double pointer to the thing, or a pointer to a memory location. It can take a pointer to a thing that this function will construct on our behalf, or will attempt to construct on our behalf, and will return an integer 0 for success and non-zero for failure, as is the common way that is interpreted in C. We have a free for freeing the thing, and two functions, get serial and get name, which each take pointed. Oh crikey, what am I doing? No, I see, caps lock. They both take a pointer to a thing, and serial returns the int, and get name returns the cat pointer, respectively. Okay. And I also have in this project the actual implementation of the library, just so I didn't have to install it in my system somewhere. But anyway, details. Okay, so the main function here just calls makething42 organization BFPG. So this is going to attempt to construct a thing that's going to return a maybe thing, and then we're going to do a case analysis on the maybe. If it's nothing, it means that the construction failed for some reason, probably a failed allocation, so we're going to print a message to that effect. If we do have a successful construction, then we're just going to pull the name and the serial number off the thing, and we're just going to print the message. So yeah, really brain dead simple. We're just going to construct an object in the C library, and then call some functions to get the information from that object, and print some information, and that's it, we're done. The binding is in this file here, so we have find function interface. We're exporting only makething, get serial, and get name. So we don't actually want to export the raw imports, because these are not really, I mean, you don't want to use a function like that in Haskell. It's a reality of writing the binding, but you don't have to export it from your binding. You can do something much nicer, like makething with the type int the string to IO maybe thing. So you want to deal with native Haskell types and Haskell, or abstractions commonly used in Haskell, like maybe for failure, when you may or may not have a thing, rather than an integer that says whether something succeeded or failed. So we have makething here, which basically follows exactly the pattern that you saw on the earlier slides. GetName calls thingGetName and then peeks the string to marshal it into a Haskell string. And getSerial does the same thing, but for thingGetSerial, and no marshalling is needed. We just call from integral to turn it into any numeric type. Our foreign imports are, again, pretty straightforward. Just foreign import C call the names of the functions respectively and their types. And here we do that thing which is not recommended, where we have type thing is pointer unit. Now there's only one type that we're dealing with in this library, so maybe it's not an issue, but if there were more types, or if I was binding to multiple different libraries in my program, then this is something you definitely want to avoid, because this will let you shoot yourself in the foot. Okay, so let's apply a healthy dose. Well, actually, let me first compile this and run this to prove that it works. So I'll just do cabal run.
Sick fault.
That did happen a few times. I'll show you why that happened too. In my C library, I forgot to do this. So I built the object, but then I forgot to write the pointer back to the location provided. And I was like, why is it always segfaulting? Yeah, it's been a while since I exercised my C legs. Yeah, so cabal run. Oh yeah, it ran. Yep, good. Oh well, I'll just run it again. Man, this laptop is slow. Cool. So yeah, we print made a thing, and then 42 BFPG. So it's just the stuff we read off the C object. Okay, so the first thing we can do when we are going to apply some C2HS to kind of shrink the amount of boilerplate in this binding is to write a pointer directive for things. So I'll say pointer thing t as thing. So we can get rid of that and get rid of those foreign imports, and we're going to replace them with calls. So call directive thing new, and we had thing get name and thing get serial. Okay, now we have a foreign import here for the destructor as well, or the free function, but we're not using that just yet. Okay, so let's see if this runs. Oh.
Hello? Yeah.
I know what I did.
Cool.
These are pure functions, so we have to use the pure keyword there.
Cool, yeah, we'll do that right now.
Okay.
You didn't tell them they're going to be early or late. Sorry?
So that built. Let's have a look at what our C2HS expanded into. So just do a tabby dist build demo temp. Okay, so this is the output from C2HS. You can see generated by C to Haskell compiler version 017, blah blah blah. Edit the original CHS file instead. Yep, that's good advice, but we want to just look at what is created here. So type thing is just a pointer unit, and the call directives have just been replaced with the name of the function that was imported, and all of our foreign imports have appeared down the bottom. Okay, so now we want to avoid that pointer unit, so we just add new type to the end there, and then I think here we will need to wrap that up, so we'll apply just the thing. Now if we build this, it's not going to build, and there's a weird problem, and so it's saying expected type pointer to thing, actual type pointer thing. So what's going on here? So this here says pointer thing where we really wanted to say pointer to thing, and I don't know why that's happening. I'm not sure if it's a bug, but anyway, I'm going to follow up and ask a question on Stack Overflow and try and work out why this is happening. Because if we now add foreign here to turn this into a foreign pointer, and if we add our new foreign pointer thing free, now if we run this, it's still not going to type check. There's a couple other things I need to change. The first argument of peak, namely pointer. So why has this happened? Peak pointer. Ah, I know. What I need to do is peak pointer turns an IOA, and new foreign pointer also returns an IO, so I actually need to do a bind here. So we're going to peak pointer and then bind fmap just the thing, foreign pointer thing free. Okay, so that should get us past where we were before. The only thing that remains, I think, is just to use the with thing to unwrap the foreign pointer. Oh, no. So what's going on now? So IO maybe thing. Well, let's just have a quick look at what it's generated. Yeah, that's not right. So, pointer thing, TS thing, foreign new type. Don't you just love live demos? And really slow laptops. Okay, 24, 28. Couldn't match IO maybe thing with maybe thing. Expected type point thing. Actual type point thing to maybe thing. Line 24, so I have a peak pointer, I'm just going to return an IOA. Do not just the thing, new foreign pointer thing free. Yes, okay, so that solved the problem there. And then down here, what we're going to want to do is, so get serial here, we're going to want to with thing, we should find that with thing has been provided for us because it's now a foreign new type pointer declaration. So it's going to call with thing. Can't even remember what goes here now. Anyway, you get the idea. So you can see that we've gone from using the FFI directly without any automation of the boilerplate to using just a type alias with the pointer declaration without new type or foreign, and then that allowed us to remove those explicit foreign imports and just use the call directive so that C2HS would write them for us. And then we've gone up to a new type, which didn't work because of things I don't understand why they're not working. And then foreign pointer, which works, but we still have a little bit more work to do to fix up these functions. Okay, so hopefully that was somewhat instructive to people. Right. So just a little bit more to get through. So some other tools, Cabal has support, as you saw. I was using Cabal there to build that project. So you should supply the build tools directive and C2HS, which will just add C2HS as a build dependency for your project. Just move that pointer away. And yeah, if you're binding to libraries, just in your system libraries, you may need the extra libraries directive to say, yeah, I want to link to lib not much or lib whatever it is you're linking to. Right, there's another tool called HSC2HS. Its file extension is .hsc as opposed to .chs, which is the C2HS file extension. So it does mostly the same stuff, but it does it in a different way. So HSC2HS actually builds a program and then uses that, builds a program that included the header file that you're interested in and use that program to spit out Haskell code, whereas C2HS works purely by parsing the header file and doesn't actually build a program with it. So as a result of HSC2HS's strategy of building a program, it means that you can find out what defines were, and you can bind to macros and constants that you can't actually do with C2HS. It also provides better storable boilerplate automation for the same reason. For example, you can have that program that it builds tell you what the size of int or the size of long is on the platform you're building on, whereas you can't get that just from reading a header file. But otherwise, C2HS is more powerful and can do more for you. Some people actually use both in the same project, so they'll have two separate binding modules, one for getting the things that C2HS is good at getting at, and a different module for the things that C2HS is good at getting at, and then they'll just import both the modules, which is pretty full on, but some people are doing that. There's a useful, informative discussion of the differences on Stack Overflow. That's the link. The slides will be up later. So more tools. There's also C2HSC. This doesn't get confusing at all, right? So this takes a header file and builds a .hsc, which can then be used for processing with HSC to HS. Bindings DSL is a bunch of C preprocessor macros to help you write the bindings, and language C inline, which there was a talk on that at Lambda Jam last year here in Brisbane, and it gives you ways to call C and Objective-C inline via template Haskell, and that's the link to that tool. Okay, so what have we covered? We've covered FFIs. What are they? We've looked at how to use the Haskell CFFI directly. We've seen some C2HS examples, so some simple examples of how to avoid writing a lot of boilerplate when you're writing libraries, bindings to libraries. We had a brief overview of some of the other tools in this space. And hopefully now you can write a binding or work on a binding. I just had a great report from Ben, who said that after the practice session he was empowered to look into some bindings for some LDAP stuff that he's using. So yeah, that's cool. Hopefully for you now, if I've actually told you anything useful and done a good job of it, then you should know enough to get into FFI work in Haskell. There's plenty that we didn't cover. So we didn't cover how to call Haskell from C, so foreign exports. We haven't covered how to deal with external garbage collectors and special allocators, and I have war stories, ask me at the pub. We didn't have much of a look at the storable type class. Certainly we didn't look at how to implement the functions for marshalling to and from memory regions. And we didn't have an in-depth look at HSC2HS or these other tools that I mentioned. And we didn't look at any other FFIs. Haskell actually has other FFIs, including JavaScript FFI, which is part of the GHC.js project. So yeah, we looked at the C FFI, but if you're interested in binding to other languages, there might be an FFI for you, or maybe you'd like to write one or ask someone to write one if you're really, really hardcore. So resources, the FFI report or the FFI chapter of the Haskell 2010 report. There's a Wikibooks book on Haskell, which includes a chapter on the FFI. The FFI cookbook is really handy, so it contains a lot of instructive examples, in particular for dealing with common C idioms. The C2HS documentation is at this link. Again, these slides will be up a bit later. And that documentation is pretty comprehensive. There's a lot of options to the directives, like the enum directive and the pointer, the call directive, that I didn't cover this evening. So if you are going to use the FFI and use C2HS, I encourage you to read that in full. And that's my not much library. Cool. Thanks for listening.
The storable type class, it obviously has some concept of endianness.
Does it mean you can't use it for networking stuff if your architecture doesn't line up to network ordering? And is it,
Don't know.
okay.
Yeah, I'm not sure. I mean, if you have a degree of confidence in the end-uness of the systems that will be communicating, then it shouldn't be an issue, but it's probably not something that you would want to do blindly, that's
Yeah.
for sure.
Just put it over the socket.
Yeah.
Hope
No,
for the best.
Don't do that.
Cool.
Or maybe do it, but hope for the best and plan for the worst. I don't know. Yo.
I noticed when you were calling your C APIs, for some reason, thing free had like an Ampersand in front of it. Why is that?
Yeah, okay, great question. So I'll just, what's that? Yeah. So the ampersand refers to the address of a symbol in C. So it's kind of the opposite of a pointer. A pointer says this is pointing to a memory location. Ampersand says I want the memory location of this. So this is, finalizer pointer is, did I actually include what it's an alias for? Yeah. So it's a function pointer. So in order to get a function pointer, you need a pointer to the function. The way we get that is we use the ampersand operator to say, please give me the address of this function.
It's different from the other ones. Where, how is that one function different from all the other functions? That's
Right.
something that I didn't quite grasp.
It's because we actually don't want to call this function ourselves. We want to pass the function to another facility, in this case Haskell's garbage collector, and give it the ability to call a function.
All right. Yes, it is doing something completely different. Okay.
Cool.
It's the C functional programming.
Yeah.
Yeah. First class functions, really. Yes.
What happens if you call a C function that takes 10 seconds to run in terms of concurrency of the scheduler in the runtime?
Yep. Use safe, and then you'll have no problems. You know, so you can use fork.io to have a green thread in Haskell. Call safe. You're not going to have any issues at all. Even if you, even if you only have one physical CPU, it can be preempted. Whereas if you don't use safe, or if you use unsafe, because safe is the default, the Haskell runtime cannot preempt that thread. So basically just use safe if you are aware that a function may take a long time to complete or block. Yep.
So that would count for both CPU and IO bound functions?
Yeah, any blocking at all. Yep. Okay,
Cool.
let's go.
Thanks,
Pizza.
Fraser.
Cheers.